Okay, we are online. I will do a short introduction and then I will pass you the floor, okay?
Okay.
Welcome everyone. Today we have another talk in our webinar series, and today we have Sunil Mucesh from the University College London talking about the machine learning approach to study galaxy properties. This webinar is also being streamed live on YouTube. You can find the link, or you can access the link in our YouTube channel /LIneA MCTI. So Sunil, thank you very much for being with us today. The floor is yours.
Thank you. I'll share my screen.
Okay.
So, yeah. So, can you see the screen?
Yes, we can see.
Okay, so yeah, hi everyone, my name is Sunil. I'm a PhD student at University College London. And first of all, I would like to say thank you for inviting me to give this talk. So today I'll be presenting my research, which is on using machine learning to estimate galaxy properties, in particular probability distributions. And in particular, I've focused on joint redshift-stellar mass PDFs and how to derive these using a machine learning algorithm called random forest. So I worked on this project with my supervisors, Professor Ofer Lahov and Dr. Will Hartley, and other collaborators. So what's the motivation behind this project? Well, when you try to estimate galaxy properties using a few photometric bands, they're imprecise. And we want to fully characterize this uncertainty in the estimates. And to do so, we require probability distribution functions, or PDFs. And so far, the focus has been on generating redshift PDFs. So it has been shown that using redshift PDFs instead of point estimates can improve the accuracy of cosmological measurements. But you can think of a galaxy as, you can describe a galaxy essentially using a multivariate PDF of both redshift and physical properties. So recently there has been a new influx, a new class of SED/template fitting codes, such as Bagpipes, Beagle, Bayes SED, and they use a Bayesian approach to derive these multivariate PDFs. So there's two advantages with deriving these multivariate PDFs, is that you're essentially accounting for the correlations which exist between these galaxy properties, and you're able to incorporate the uncertainty in redshift when to derive the other physical properties. The only disadvantage is that these methods are not very efficient for generating large number PDFs for a large number of galaxies. So we tried to solve this problem using a machine learning based approach. So machine learning has been shown to generate these PDFs very quickly. And in particular, we focused on joint redshift-stellar mass probability distributions. One, because due to their applications, there are many applications. And secondly, redshift and stellar mass are two of the most robust properties to predict as opposed to the others. So yeah, we used random forest. It's an ensemble supervised machine learning algorithm, and it's based on decision trees. There's many reasons we chose this algorithm instead of the others. So it's very easy to implement, and it's done. So it's not a black box. It generalizes well, so it's resistant to overfitting, and it can be used for both regression and classification tasks. And recently, it was used to predict stellar mass and star formation rates of galaxies. And previously, it was used to predict point estimates and probability distributions of redshift. So as I said, random forest is based on decision trees. So what is a decision tree? Well, you can think of a decision tree as a data structure which allows you to make decision. So let's take the silly example. You want to decide if you want to take, your umbrella with you when you're going out to work or to office. So the first question, or the main question you could ask is it raining outside? And if the answer is no, then you don't need an umbrella. But if the answer is yes, then you might ask a second question. Will I spend most of my time outside? And if the answer is no to that question, then you're probably good with that one. But if the answer is yes, then you probably should take the umbrella. So decision trees are very intuitive, and this is kind of the structure of a decision tree. So at the top, you have a root node. Then the nodes after that are called decision nodes, and your final predictions or classifications are in these leaf nodes. So how do you build a decision tree from data? Well, you use this algorithm, and the job of this algorithm is to essentially cluster or group data with similar properties. So in this toy example, we have blue data points and green data points, and we want to identify the groups. So we can visually see that if we make the split at 2, then we're able to separate these two groups. But for higher dimensional data, it becomes very difficult. So we use this algorithm and to essentially decide where to make the split and which split is the best, we use a loss function. And for regression trees, the loss function is based on the variance. So in this case, the S is a loss function for you can use to build regression trees. So in this case, to identify these two groups, what we would do is take the I value for a single galaxy, minus it from the average of this group, so ym, and repeat this for all the data points on this side for this group M. And then we would repeat the same process on this side, so for the green points. And we essentially make the split where this sum is minimized, so the variance is minimized. So to choose essentially where to make the split, we go through each feature in our data set and different locations. And we essentially make the split where this variance is minimized. And you repeat this process continually until you reach some threshold. So in this case, we only needed a single split. So once you've built the decision tree, you can use it to make predictions for new data. So let's imagine that we have a new data point which lies over here. Then we can pass it down to the decision tree, and we can ask, is the value of that data point less than 2? If it is, then it belongs to this group, and we can use the average value of this group to make a prediction for that new data. So random forest is it's essentially many of these decision trees, and with a few tweaks in the algorithm. So first, you sample randomly from your data with replacement. So you have your training data, and you choose a subset from that data set. Next, you choose a subset of input features. So these could be colors from which you build your decision tree. So you choose, you have your bootstrap data, and the chosen features, and then you repeat, you run the algorithm which I described in the previous slide to get a single decision tree. And you repeat this many times to get an ensemble. And this is essentially what the random forest is. So once your random forest has been trained, you can use it to make a prediction. So you pass a new data point down all of these decision trees. And if you're doing classification, then you can just get the majority vote. You can use a majority vote as your classification. And if you're doing regression, then you can just average the values from the different trees to get your final result. So how do we use random forest to build joint redshift-stellar mass probability distributions? Well, we know galaxies will cluster together in n-dimensional space if they have similar values of input features, so colors. And random forest will try to find these clusters by minimizing the loss function with redshift and stellar mass as the target variable, so y. And these clusters end up in the leaf nodes of the decision trees. So the leaf nodes will then contain redshifts and stellar masses of similar galaxies. So once this forest has been trained, we can pass a new galaxy down all the decision trees, and it should end up in leaf nodes that are representative. So leaf nodes that are similar represent the galaxies in question. So first, we can easily extract point estimates by averaging the redshift and stellar mass values of the training galaxies in the leaf node. To build marginal probability distributions, we can aggregate all the redshifts and stellar masses in all the decision trees. And we can build joint PDF simply by combining the aggregated values. So we need training data sets to train our random forest model. And in this case, we've used 3. So the Dark Energy Survey Year 3 Deep Fields dataset, the DES Year 3 Balrog dataset, and the Cosmos 2015 catalog from LAGEL. So the Year 3 Deep Field catalog, it contains deep and precise photometry in the GRI-Z bands of more than 1.7 million objects. So we can use these as our input features. And we combine this data set with the Cosmos 2015 catalog, which has accurate redshifts and stellar masses for our target features. The only problem is that we want to be able to essentially build these PDFs for galaxies in the main wide field dark energy survey. And if you try to train a random forest model using the deep field, then it wouldn't be able to do well because the errors, the photometric errors present in the deep field are different compared to those in the wide field dataset. And the other solution would have been to essentially use a wide field catalog, but we cannot do this because the Cosmos field, it does not overlap with the main survey area, so we do not have access to the accurate redshifts and stellar masses. And even if we try to estimate this using he's using the full band wide field data, they'd be imprecise compared to those in the Cosmos catalog. So to solve this problem, we essentially required a catalog of deep field galaxies which mimic or emulate galaxies in the wide field. And this led us to Balrog. So Balrog is a Python package to measure the transfer function of imaging survey. And from this, we use the DES Year 3 Balrog catalog. So this catalog has been produced by injecting model fits of galaxies drawn from the Year 3 deep field, and they injected into DES Year 3 single epoch images. So Next, the DES measurement pipeline has been run on these images, and this has produced the DES Y3 catalog, which has the true and the measured photometry in GRIZ bands. So essentially, we have now the ready-made catalog we need which emulates galaxies in our target field. So the DES Y3 gold dataset. So we combine this with the Cosmos 2015, and this allows us to produce what we call the wide field or WF dataset. So to produce these datasets, we apply a few simple cuts. We apply a cut in the I band at 23.5. We apply a redshift cut to essentially remove galaxies with erroneous redshifts and stellar masses. And we apply this flag to remove any galaxies which have erroneous flux measurements. Next, we convert these fluxes in the catalog into 1/8" magnitudes or longitudes to essentially avoid removing any galaxies which have close to 0 or negative fluxes. And finally, we perform a split on both of these datasets to produce a training and test dataset. So the deep field and wide field training datasets, they contain approximately 42,000 and 314,000 galaxies. And the testing datasets, they contain approximately 10,000 or so galaxies. And this plot just shows the redshift and stellar mass distribution along with the distribution, the GRZ longitude distribution. So we built two random forest models, which we called DES deep field, DF, and DES wide field, WF. So the DES deep field model, it allows us to essentially measure the baseline performance. And the DES wide field, we train using the wide field dataset to produce joint PDFs of galaxies in our target dataset. So we build a single model, well, two models, and we predict both redshift and stellar mass simultaneously. And the input features we use are the longitudes, the colors, the G minus R, R minus I, and R minus Z, and the errors on both. And the first thing we did was extract point estimates. So here I've plotted the true redshift and stellar mass from the Cosmos catalog against the predicted by the machine learning model. So in this case, we can see that most of the data points, they lie close to the diagonal, which indicates that the predictions are accurate. So in the top panel are the results from the DES DF model, and in the bottom panel are the results from the DES WF model. The main difference is that there's more scatter with the DES wide field model, and this is essentially because we're using degraded photometry in this model compared to the precise photometry that we input into the DES deep field model. There are outliers at a low and high redshifts, but they're essentially due to a combination of degeneracies which exist in the color redshift space and due to a lack of training data available in these regions. So it's very easy to validate point estimates because we have like the true estimates which we can use for comparison. This is not the case with probability distributions. So we don't have a true PDF that we can use to validate them. So it's not possible to validate individual PDFs, but we can determine their overall validity. So how accurate are the probability distributions on average? And for this, we use a framework, and we use two different modes of calibration, probabilistic and marginal, which I will explain in these slides. So the idea behind probabilistic calibration is that the true values of redshift and stellar mass should be random draws from their respective PDFs. So we can determine this using or by computing the probability integral transform, or the PIT, which is essentially the area under the probability distribution up to the true value. So in this case, I've just plotted a redshift distribution, and the yellow line indicates the true value from the Cosmos catalog. So I would work out the area up to this point and repeat this for all the PDFs. So you can imagine that if the true values are random draws, then the PIT value will be a number between 0 and 1. And for an ensemble of galaxies, the distribution of these values should follow the standard uniform distribution. So these are exactly the plots we get from the calibration. So I've plotted the PIT distribution. On top, I've essentially made a QQ plot, which allows us to visually see if there's a divergence from uniformity. So if this blue line is close to this black diagonal line, then the distributions are uniform. To quantify this, I've also computed a few metrics. So the Kullback-Leibler divergence, the Kolmogorov-Smirnov test, and the Kramer one misses metric. So the idea here, or the key takeaway here, is that if these values are close to 0, then the distribution, the PIT distribution, is uniform. So once again, in the top panel, I've plotted the distributions of redshift and stellar mass from DES-DF, and in the bottom is from DES-Whitefield. So we can see that the distributions are very uniform. There's low number of catastrophic outliers, and in this metric, DES-DF is performing marginally better, but there isn't a huge difference. Overall, the distributions are very uniform. So the PDFs, the marginal PDFs, are calibrated in this mode. So sometimes you can end up with a uniform distribution, even though the PDFs are biased. So in this instance, you can run a second mode of calibration, and this is what we do. This is called marginal calibration, and the idea here is that the average predictive CDF, so Fi in this case, it should match the true empirical CDF, GI. So how do we compute this? We have a distribution, and we evaluate this distribution at different values y. So for example, in this case, I would evaluate this distribution at different intervals in this redshift range. And we repeat this for all the probability distributions to get the sum. With the true empirical CDF, we essentially do the same process, but with the true values of redshift and stellar mass. And to essentially see what's happening, I've plotted these two distributions, so FI and GI. And if the PDFs are not biased, then these two distributions should match. So this is exactly what we see in this case. And we can do a bit better and essentially plot the difference in these two CDFs at different points. And if the distributions match, then we should only see small fluctuations about this zero line. And this is exactly what we see in these plots. So the PDFs, the marginal PDFs of redshift and stellar mass are calibrated in this mode as well. So these are kind of like the key plots, the joint PDFs, which we build or which we generate. And I've plotted two distributions of a galaxy. So a galaxy in the deep field test data set, and its counterpart in the wide field test data set. The yellow star is the true redshift and stellar mass value, and the white star is the average from the machine learning model. And the green dots are the samples from the posterior, which we use to build this probability distribution. So the first thing we can see is that for these galaxies, the joint PDFs, they occupy similar regions of redshift and stellar mass space, which is what we want. The key difference is that this deep field model is producing more compact PDFs, and this is essentially a reflection of the precise photometry we've used to train the model. Okay, so how do we validate joint PDFs? So if we try validating the joint PDFs using the metrics or the methods I've used to validate marginal PDFs, they won't be they can no longer be applied. So if we run the same analysis and get the PIT distribution for joint PDFs, it's no longer the case that it will be uniform, even if the joint PDFs are calibrated. So we use the multivariate extensions of these two modes of calibration, so probabilistic and marginal, which are called probabilistic copula calibration and Kendall calibration to validate our joint PDFs. The advantage of using these modes of calibration is that they can be interpreted in the same manner as the univariate counterparts. So before we had probabilistic calibration, now we have probabilistic copula calibration, and we assess this using the copula probability integral transform, or the COP-PIT. So the COP-PIT is the Kendall distribution function, KH, evaluated at the joint CDF H, which is evaluated at the true value of redshift and stellar mass Y with this tilde hat. So this Kendall distribution function KH is then just the CDF of the joint CDFs. So that's a bit tricky to understand. So I'll show how we essentially compute this COP-PIT in practice. So as I said, the COP-PIT is the multivariate analog of the PIT distribution. And to compute this, let's consider this this plot or this animation. So, for example, assume that we have these are the samples from a distribution. So what we do first is at each of these points, we essentially work out the CDF HY by summing the number of points to the left and to the bottom of the point we've selected. Once we've done that, we essentially have, so in this case, we have the empirical Kendall distribution function, which is this red curve. Next, we do the same process, but we, for example, imagine that the true value of redshift-stellar mass is here. We work out the CDF at that point, and we see where it lies in the Kendall distribution function. So in this red case, and we get the CDF at that point, and this is essentially our copula value. So you can imagine if the redshift and stellar mass are random draws from this joint probability distribution, then copula will essentially be a number between 0 and 1, and the distribution of these values should be uniform if the joint PDFs are calibrated. And these are the copula distributions. So the same as the PIT, but they can be interpreted in the same manner. So we have the copula distribution for DES-DF and DES-wide field. And once again, we can see that they're very uniform. So this tells us that the joint PDFs are calibrated in this metric or in this mode of calibration. So Kendall calibration is the multivariate analog of marginal calibration, and it's essentially probing how well the dependent structure or the relationship between redshift and stellar mass is predicted on average. So we can assess this by comparing what we call the average Kendall distribution function, this KHI, to the empirical joint CDF JI of the predicted joint CDF's HI evaluated at the true redshift and stellar masses. So if we compute this two distributions and we plot them along the probability space from 0 to 1, we get a similar plot to the one we had for marginal calibration, where once again, if the fluctuations about the zero line are small, then the dependent structure between redshift and stellar mass is predicted well on average. So in this metric, we can see that the DES wide field model is performing better than the DES deep field. And this is due to the fact that, well, what we think is it's because we've trained DES wide field on a data set which contains multiple scattered copies of the deep field galaxies. And this is enabling it to predict the structure between redshift and stellar mass better than DES wide field. So to test this, we ran a rough analysis where instead of just using the deep field dataset, we scatter each deep field galaxy according to its error and then train a random forest model. And when we did this test, what we found was that this violet curve became similar to this pink curve. So it started to perform better in this metric. Okay, so the plots and the metrics I've showed so far are, I understand, are difficult to fully appreciate without, putting them into familiar context. So we tried to compare The results we achieve using our method to a standard SED fitting method. So in this case, we use bagpipes or Bayesian analysis of galaxies for physical inference and parameter estimation. And this code, it generates a complex model galaxy spectra, and it fits these models to spectroscopic or photometric data to infer galaxy properties. And within the code, it's using the multi-nest sampling algorithm to generate the multivariate probability distributions of redshift and physical properties. So we run bagpipes twice. The first run, we run it on test galaxies in the deep field dataset, where we input photometry in Subaru V, R, I, and Z bands from the Cosmos catalog. And to validate these posterior PDFs, we do a second run, but this time we input 22 Cosmos bands, including the ones we used in the first run. And these are the results once we do the analysis. So we have essentially all the diagnostic plots, the PIT distribution of redshift and stellar mass, the COP-PIT distribution, the Marginal calibration plots of redshift and stellar mass, and the Kendall calibration for the joint PDFs. So we can see that in all of the metrics we've used, our method is performing better, which is this pink distribution, or the pink color. And it's still, bagpipes is still performing well for the redshift PIT, as it's still competitive with other template fitting codes. Okay, so from the metrics we've used, we've shown that we can generate PDFs, joint redshift stellar mass PDFs, which are calibrated. So we developed this work into a package called GALPRO. It's a Python package which is based on the random forest, and it's able to generate these PDFs of galaxy properties on the fly. The code is available on GitHub with this link, and the documentation is available on this page. So I'll quickly do a brief demo of GALPRO. So this will be a partially live demo, so hopefully everything works well. So let me try this. Right, so the first thing we do is load the packages we need. So NumPy and GALPRO. We run and load the packages. Next, we load the data. So here I'll be essentially building the DES deep field model. And these are the training and test data sets, which I load. So the input features are the longitudes, the colors, and the errors on both, and the target features are the redshift and stellar mass from the Cosmos catalog. Let's just check how many samples we have in the training and test. So we have 42,000 in the training, and in the test we have 10,000 or so galaxies. So now we can train the model with this function. So we call galprogp.model, and we pass in several parameters. So we specify the name of the model. So here I've just called it deep. We give it the training data sets, the test data sets, and this is optional. So we just, for now, I've given it a list of target features, so redshift and stellar mass, which is necessary to make the plots, which I'll show later. And finally, we can save the model. So here I'm going to save the model by specifying true. So I'm going to train the model. So it's training. It should take a minute or so. And in the meantime, I'll show what's happening in the background. So it's created this folder called GALPRO, where the script is based. And within that folder, it's created another folder called deep, which is the model name we specified. And in this folder, we have 3 separate folders, one for point estimates, another for the posteriors, and the third for the validation. So it's still running. Hopefully it's done in a couple of seconds. So yeah, it saves the model now. And if we go check back in the folder, this is essentially the folder, the model we've trained. And these are the other files we need to use the model. So this is me training from the beginning, but if you already have a trained model, then all you need to do is specify the name of that model, and it will load the model automatically. Okay, so the first thing we can do is generate point estimates using this function model.pointEstimate, and we save it as with this variable. We specify 2 parameters, whether we want to save the estimates and if you want to make scatter plots. So if I run this, so it's generated the point estimates and it's saved them in this folder, and the point estimates are in this H5 file object. But it's also returned the point estimates, and if you print those, then you can see the redshift and stellar mass values of the test galaxies we input. Next, we generate the probability distributions, and we do this using this function model.posterior. Once again, I'll specify that I want to save the posteriors. I don't want to make any plots, and I don't want to generate these PDFs on the fly. So if I run it now, it's generating the posteriors. And it saved them. So this generated PDFs for the 10,000 or so galaxies in a few seconds. So this is much faster than using standard SED fitting code, which would have taken me a few hundred hours. So it's very rapid. We can also access the probability distribution, the samples, by specifying the index. So the 0th galaxy in this case, if I run this, it's just given me the samples from the posterior. So the main or the key part of this package is the ability to generate these PDFs on the fly. So if you're able to generate these PDFs on the fly, it solves 2 issues. It's not going to run into any memory issues, and these PDFs they take up a lot of storage space. So if you're able to generate them on the fly, then you can just input this code or use this package into your research code and generate the PDFs on the fly without the need to save them to disk and then access them later on. So this is the same function, but this time I'm going to specify that I want to generate these PDFs on the fly. So by setting it to true. So if I run this, it says it's generating posteriors. These are the 2 lines of code which you need to input into research code. So you specify next posterior, and this will essentially give you the samples from the posterior distribution in order, and then you just do this in a loop. So it will generate the PDFs on the fly, one at a time, which is much faster than the previous method I've showed. So yeah, I'm not going to go through this, but the final part is the validation. So you can run validation. You can validate your PDFs or your models in the package. using this validate function. And I'm not going to run this now because it takes a bit of time. So I'm just going to move on to the last part, which is generating plots. So you can generate various plots using GALPRO. So for example, you can generate scatter plots. So if I run this now, says it's creating the scatter plots, and these are the plots I showed in the presentation. So I've saved them to disk, and I've also showed them in this notebook. If you're just predicting redshift, or if you had a single target variable, then you could run this plot.marginal, and it would plot the marginal PDFs. In our case, we have joint distributions. So if we run this, then it should start creating the plots, which it has done. And alternatively, you can run this plot corner if you have 2 or more target variables. So it will do the same thing, but for 2 or more variables. So it's creating the plots, and hopefully this shouldn't take long. Yep, so it's started producing these plots. And these are the standard validation plots, which you can also make, which I showed in the presentation. So the PIT distributions, the marginal calibration, the COP PIT plot, and the Kendall calibration. So I'll quickly go back to the presentation and talk about some applications. So joint redshift-stellar mass, they have many applications. For example, you can use these PDFs to study the evolution of the stellar mass function. Another interesting application could be to use GALPRO to generate joint redshift stellar mass, joint redshift luminosity PDFs, which you can use to measure the Hubble constant from the dark standard sirens. So these standard sirens are absolute distance indicators, and when you have, for example, the merger of 2 black holes, then it will produce these gravitational waves, and from them you can measure the Hubble constant. And in recent papers, it has been shown that using a full redshift PDF can improve these measurements. So if you input now the joint redshift luminosity PDF, then you're able to define the selection function of your galaxy sample. So I know I'm probably running out of time, so I'll just leave a summary of the project here. Thank you.
Thank you very much, Sunil, for the very interesting talk. We now have time for questions from the audience. If you are on YouTube, you can put your question in the comment sections and I will redirect them to Sunil. So, questions?
Hi Sunil, this is Julia. Hi. Yeah, I have some questions. I will just address one and let time for other people. And then if I am lucky, I go back to ask the other ones. Okay. So I'd like to ask you about the concept of looptitudes. Could you talk a little bit more? And I would like to ask if the conversion from regular magnitudes to looptitudes is included in your package?
Okay, so the first question, what are looptitudes? So when you have faint galaxies, let me find. So when you have faint galaxies, the standard magnitude is undefined, and we cannot use this data to train a model. So what we did was convert to looptitudes. So they're essentially the same as magnitudes for relatively bright galaxies, but the value is defined for faint galaxies. So we essentially had a complete sample of galaxy. We didn't have to throw away any from our model. The second question was if the standard conversion is implemented in the package. No, at the moment, but it's very easy to do. So yeah, I can try to implement the conversion in the package, and then it will be readily available.
Thank you.
More questions?
Yes, I have a very naive and general question. So I've been thinking about uncertainties in photometric redshifts, and my question is the following. So you usually stack all the PDFs of the galaxies to get the overall redshift PDF, right? Is that correct?
Yeah. So
my question is the following: how do I interpret this? Suppose I want to generate different realizations of the PDF of the photometric redshifts. How does that change the n of z? You know, I don't know if this question is clear. I want to understand the uncertainties in n of z. So I understand that you have the PDF, which is the stacked one, but how would I generate a new realization of this? I just don't know. I'm sorry. Maybe Julia also can help me with this. I don't know. Do you guys? Very naive. Sorry.
So okay. So if we stack these PDFs, then we get n of z. And your question is how do these uncertainties affect the overall distribution? Is that correct?
Yes, so the question is really the following. So n of z enters in several observables. Like if I want to compute any two-point correlation function, I have to assume an n of z. And what people usually do is that they take just one parameter, which is just a shift in the redshift distribution to parameterize the uncertainty. Now, if I really want to do a more complete job, in the sense of, what are the uncertain, the probabilistic uncertainties. So I have one realization of n of z. How do I generate another realization of n of z? That's my question.
I'm not sure. I'm trying to think.
I don't even know if this question makes sense, because I really want to understand the impact of n of z uncertainties in the two-point correlation functions. But I don't know how to do this because I don't know what that means. The stacked PDF, I don't know what that means. Sorry.
I think there are metrics to see if your n of z is calibrated, but I can't remember. Sorry, I can't remember anything at the moment. That's
okay. I hope someone can help me in the near future. Thank you.
I also don't have the answer, but I know that Alex Maus did a work related to that, and I can find his paper and send to you the link.
That would be helpful, Julia. Thank you. And
sorry, I couldn't answer your question.
Thank you, Sunil.
Any more questions? Well, I have a more machine-related question, if I may. There's this situation where with bias in, bias out, when you do some training and modeling, for those who are starting, who only have a grasp like on studying galaxy properties, what will be what should I be careful with when using a machine learning approach because of the biases?
Okay, so one thing you want to make sure is your training data set is complete, because if it's not, then if it doesn't, if you input a test object which it's never seen before, then it will try to extrapolate, and this is what we don't want. So I think that's the major thing. You want your training data set, your prior knowledge to be complete, and or as good as complete and representative of the analysis which you'll use for where you use the galaxy properties in your analysis. Yeah, so if your data is rubbish and biased, then you can quickly identify that using the metrics I've showed. So for example, if your PDFs are not calibrated, so for example, in this case, then you're able to use these different metrics to see if your model is going to perform well on your test or target data set. If that makes sense.
Yes, it does. Thank you. Thank you very much. We still have time for questions. Julia had another question.
Yes, I have two questions. Can you go back to slide number 15? Yeah, so this plot on the left side, is an example for one galaxy, or is this the redshift distribution of the total sample?
So this plot?
On the left side. Yeah, both.
Okay, so this is for a single galaxy. So it's just the distribution, the marginal distribution of redshift for a single galaxy. And this plot is for the entire PDFs. So it's kind of the stacked PDF.
Okay.
So we want to compare this to the true, which is what we get from Cosmos. And if the distributions match, which they should, then the PDFs are calibrated. And this is what we see in this case.
Okay, it makes sense. And then can you go to slide number 21? Between 21 and 23, it's about the question is about the size of the validation set. So does this Kendall calibration, I suppose, for you to have a uniform distribution of the truth, the distribution, you should have a minimum number of entries. So otherwise, you're going to have some noise in the distribution. It would be still uniform, but very noisy. Yeah. So I saw that you used 20% of the sample, and it's more or less 10,000 objects. The question is the same number of objects for the wide and the deep field? And would be the amplitude, the difference in amplitude in slide 23, could that be related to the size of the samples, of the two samples?
No, so we tested this where we input different number of samples. So we tried essentially reducing the training data set. We tried making sure that the model did not have access to essentially multiple scattered galaxies, and it did not make a difference. The only thing which made a difference was essentially training on scattered galaxies. So yeah, the answer is no. The size or the number of samples, they don't affect this curve. And similarly, as you said, in this case, if you have for example, 100 galaxies, then the distribution will be noisy, but it will still be uniform.
Okay, thank you.
Thank you, Julia. I think that's it. Does someone have a last question? Okay. Well, if there are no more questions, we will now wrap this up. This presentation will be available on our website and on LINEA's YouTube channel. And for the next week's webinar, we will have Eduardo Janu Pacheco from the University of São Paulo with a talk entitled The Plato Mission, Brazil Chasing Exoplanets. So thank you everyone for attending, and a special thanks to Sunil. Thank you, Sunil.
Thank you. Thank you for the invitation to present my work.
Okay, we are very grateful. Thank you.
I hope it was interesting.
Oh, it surely
That's
was.
brilliant. Yeah.
Thank you.
Nice work.
Thank you.
Thank you.
Everyone, have a great day.
Yeah.
Okay. Please, Sunil.
I'm trying to. Okay. Yeah, I think. Yeah, I'm back now.
Okay.
Okay.
Well, okay, so thank you, everyone. Everyone have a great day. Stay safe, and I hope to see you all next week.
Bye, everyone.
Bye-bye.